This conference will now be recorded.
Hi, my name is Jonathan Zhang from Facebook. This presentation is about OCP server platform feature development in an open source, open system firmware stack that is Coreboot/linuxboot. I will co-present this presentation with Johnny Lin from WinWin. This video contains two parts. I cover the first part for some slides. Johnny covers the second part for the others. This presentation is an update of what we learned in the last years in terms of requirements, challenges, what our designs are, what we worked out, and what we plan to do. It is a continuation of previous presentations given at OCP Regional Summit. With it, we hope to get feedbacks from industry colleagues on our work and to benefit others in their OSF development. It has three sections. The overview section recalls those presentations which give context. The second section is about various server features and their designs. The last one is call to action. This open system firmware from scratch presentation explained why Facebook has been working on Coreboot/linuxboot stack. What was the status? It detailed the software components involved in the build system design. In addition, our plan of enabling our partners and the community is discussed to support our philosophy of community-driven and upstream first. This presentation, OSF support for multi-socket OCP platforms, Coreboot POC, on Tioga Pass and Skylake SP, reported the work between Intel and Facebook of doing proof of concept on Intel Skylake scalable processor and on OCP platform Tioga Pass, which is a dual socket server platform using this processor. The POC was successfully concluded. The Coreboot code was upstreamed. An update will be given in this afternoon. This is an overview of OSF stack that Facebook works on. The firmware contains Intel FSP binary and a linuxboot OS. FSP does memory training and silicon init. Coreboot initializes platform, sets up system tables, and jumpstarts Linux kernel. The init run FS we use is uroot. It detects and loads target OS. It is worth to point out that the Linux kernel used in linuxboot is just a regular Linux kernel built from Linux codebase as is. On the right-hand side is our philosophy of OSF development. So I jumped through the parts that are covered by WinWin, which will be given in the second portion of this video. Now, I jumped through to this. In the server lifecycle, there are different stakeholders, such as silicon vendor, firmware vendor, owner, and user. They all need to control certain firmware configuration items at different timing with different requirements. This table gives an analysis. This slide lists some key requirements that we are working on. Configuration items can be categorized into various types. This is a non-exhaustive list of configuration items. One type of configuration items set FSP behaviors, such as whether to enable hyperthreading, such as PCIe bifurcation configuration. Since OSF firmware involves many software components, the versions of all components need to be saved for retrieval. Some of the information needs to be retrieved from BMC. And the OSF verbose level is important for debugging and for identification of faulty hardware. On the flash, we have a partition storing configuration data. This partition uses VPD format. This format is used in production at Google Chromebook, which also runs Coreboot. It has Linux tool support. In other words, user can view updated VPD data at Linux command line. This slide lists commits we developed to enhance VPD support in Coreboot and in uroot. It also lists some to-do items. We are working on bringing up of Intel next generation server chip-based OCP platform. The FSP for such chip conforms with FSP 2.1 spec. Comparing to FSP 2.0, it added FSP error handling feature. Through such feature, errors such as memory training error are reported to bootloader, so bootloader can handle and report. To support server processors, Coreboot needs to add a number of features. A server platform can have different platforms types with different PCIe topologies. Rather card also changes PCIe bifurcation. Coreboot should detect such PCIe configuration, sometimes through GPL, sometimes through BMC, sometimes through SM bus query, and then properly configure PCIe devices and their resource assignment. Coreboot also needs to create various ACPI tables for OS to work properly and efficiently, such as DMAR table for virtualization, SRA table and SLEET table for NUMA. Last but not least, the power and idle management is also very important for data center operation. Complete RAS features are necessary for data center. Some hardware errors, such as memory and correctable errors, require firmware first handling, so that errors may be recovered in firmware and errors can be handled in a timely manner. Such handling requires system to enter into system management mode in terms of x86. Therefore, it brings performance impacts to application. This kind of impact needs to be minimized as much as possible. Even though there are many discussions on SMM and its misuse, but this mechanism is going to stay for some time. The platform actions are necessary for scenarios such as hardware error injection and PCIe hot plug. There's no alternative for non-runtime SMM. Even for OS runtime SMM, the alternatives are being worked on, but not ready for prime time. Therefore, we need to support SMM in Coreboot. The support for SMM and the various SMI handlers in Coreboot is a work in progress. Roughly speaking, there are two options. One is pure native implementation, e.g. code all SMI handlers in Coreboot. Another option is to build SMM binaries from Intel binary blobs from Intel reference code and use this blob to set up SMM environment from Coreboot. Now it's call to action. This page lists references for you to know more and to participate. Both Coreboot and uroot has valuable community with regular meetings and information repository. OCP OSF project also has a regular meeting that we meet and discuss every 2 weeks. We hope to collaborate with you. Thank you. Bye.
Hi, I'm Johnny Lin from Wiwin. In this topic, we'll talk about the OCP server platform development on Coreboot linuxboot with Facebook. Here's the overview. You can check the Open System Firmware from Scratch presentation from Facebook made in OCP Regional Summit 2019. It can give you a background on Open System Firmware development on Coreboot linuxboot and why they are doing this. Our works on Coreboot linuxboot mainly was from we're doing the development on Wiwin Breeze-Cannon storage server, and now we're moving our works to the Wiwin Tiago Pass Intel Skylake server. You can see the product information on the OCP website pages. There are many server features for system firmware, such as BMC interaction, which is very important. And during system booting, there are several IPMI interaction between system firmware and BMC. And here are the lists. For example, get BMC self-test result, start and stop FRP2 timer, and system firmware notify BMC system booting state, such as post-start, post-end. And system firmware sometimes need to write cell records, system event logs for important events. And set information to BMC, such as setting system firmware version machine configuration like processor, memory DIMM information, and bootloader to BMC. And getting information from BMC such as read-through data, get chassis power status, cell, and bootloader. From the implementation aspect, the BMC interaction, if we take UEFI PI booting phases as a reference, roughly the Coreboot can be mapped to the PI phase, and the URoot can be mapped to the Dixie and the BDS phase. So the features implemented in PI phase can be done in Coreboot. The interaction done in Dixie phase and BDS phase can be implemented in URoot. So roughly, in Coreboot, we chose to implement things like those things, like memory initialization error cell, post start, FRB2 timer start, update SMBus data according to through. It's pretty straightforward to update SMBus in Coreboot. CMOS clear. In Coreboot, right now we simply reset the RTC data, but in the future, if VPD data can be written in URoot, we may also reset VPD data. In URoot part, we implement stop FRB2 timer. Set machine information, pretty straightforward in URoot that can read SMBus and set machine information to system firmware. And setting post end. And in URoot, it provides an interactive shell that you can run commands for displaying information via IPMI. It can be a replacement for the setup menu in BIOS. Here we list some implementation examples. In Coreboot, the first part is the IPMI driver implementation. We added some IPMI driver functions to the Coreboot IPMI driver, such as get BMC self-test result, get IPMI, get system GUI, and add read-through functions. You can check the links for the implementation details. And the second part is you can call those functions, those IPMI functions from your mainboard code. Here in the example, the mainboard is monolith. So here we call the IPMI driver function to get the information from BMC and overwrite to the SMBus data. The BMC integration in URoot part. The challenge was, at first we tried to add a statically linked IPMI binary to URoot, but the size is too big, 4 megabytes. In monolith, 4 megabyte already takes half of the flash size. So, and also it's more ideal that we can upstream to URoot. So with Facebook, we developed an IPMI package written in Go. So you can make IPMI commands code in Golang directly. And also we add a small IPMI dump utility, command line utility in URoot. So you can run the command to display IPMI information. The challenge, there are several platform-specific BMC integration, such as some OEM IPMI commands. So how do we integrate those platform-specific commands? Here we add a product list table, a product list to system boot in URoot. The system boot is a URoot package that is executed by init daemon. So in system boot, it can read the platform information from SMBus and compare to the product list. If there's a match, it can run the platform-specific OEM command. And SMBus, is mentioned before, it's a very important server features. It provides the management information by system firmware. And here it can be created in Coreboot RAM stage. For memory-related SMBus type 17, it relies on Intel FSP to provide the memory DIMM information. And for update SMBus data from BMC IPMI, we need to read the correct product, board, and chassis information from BMC through. And then we can update them to the SMBus type 1, 2, and 3. You can check the previous slides for the implementation details. And other SMBus can be created by the existing Coreboot framework for your customization. And for server features, OCP. Similarly, it can be created in Coreboot RAM stage with the existing framework, such as SPMI, which is very important because it provides the BMC system interface. HPET, it provides the high precision event timer. And NUMA related tables such as SRAT, SLIT, it rely on Intel FSP to provide the NUMA configuration. And the current major challenges in OCP is the ACP Platform Error Interfaces, APEI. These 4 tables depend on SMM handler readiness, and right now we are still lacking the SMM handler implementation. And here's the call to action. The Coreboot and uroot, you can check the links for more information. And here's the link to Open System Firmware project. Thank you.
WeWin, your best choice for workload optimization and TCO.